Okay, let's revisit the nucleus. First, let's talk a little bit of a hydrogen atom, which is made up of just an electron and a proton. What holds the electron in orbit? It is the Coulomb force. F, if you recall, is K Q1 Q2 over R squared. The distance R is about 10 to the minus 10 meters. It's about half of that, 0.5, so you get the idea. In terms of energy, if we express this in terms of energy, the binding energy of the electron is 13.6 electron volts. Now, for the simplest nucleus, a deuteron, which is made up of just a neutron and a proton. Neutron and a proton, like we have here. So in this case, the only force that's present to hold the nucleus together is what we call the very strong force. The binding energy of a deuteron is 2.2 10 to the 6 electron volts. Now look at the difference here. We are going from 13 electron volts to 2.2 10 to the 6. That's about 200,000 times bigger. So the binding energy of the nucleus is much bigger than the binding energy of an atom. We are not going to get into much detail about this, but from what I hope you recall, atoms have a structure that's determined by certain rules. Those rules determine for us how many electrons do we have in each of the shells. Among those rules is the Pauli exclusion principle that tells you that you cannot have two identical electrons in the same state. That's at the same shell and having the same other properties. So at least if they share the same properties with everything, then they have the spin that should be different. One would have a spin up and one would have a spin down. We have a similar structure in the nucleus. So the nucleon distribution inside the nucleus is going to be governed by similar rules as the rules that we have for the electrons in the electron shell. However, here we have two types of nucleons, neutrons and protons, so the rules are applied separately for each. We are not getting into much detail, but one thing that I would like to mention, like electrons, nucleons have spin. So they are going to have a 1/2 spin up and down. The lowest energy state is favored for a state where n is equal to z. But as the nuclei get larger, because the protons repel one another with the Coulomb force, and because the strong nuclear force has a limited range, we are going to need to have more and more neutrons. So actually, as the nucleus gets larger, you notice here the number of neutrons is larger than the number of protons. Okay, so this is the n equals z line, and we have it preserved at the bottom here, but as the nucleus gets larger, the disparity increases. Now, a few other comparisons. For a hydrogen atom, the size, as I mentioned earlier, is about 0.5 10 to the minus 10. 10 to the minus 10 is an angstrom, what we call an angstrom. So it's about half an angstrom, or 5.29 10 to the minus 11 meters. The size of the nucleus is much smaller. Actually, it is given by this expression approximately. Is 1.2 10 to the minus 15 meters times the nucleon number to the power 1/3. 10 to the minus 15 meters is what we call a femtometer or a Fermi. So for example, aluminum has a radius of about 3.6 10 to the minus 15 meters. So 1.2 10 to the minus 15 times 27 to the power 1/3. Look at the difference between 10 to the minus 11 to 10 to the minus 15. 10,000 times smaller with a binding energy, it's 100,000 times larger.